In Lesson 3.2, you'll be looking at rational numbers, and you'll be able to write rational numbers as fractions and identify and classify rational numbers. Your vocabulary word for Lesson 3.2 is rational numbers, and any number that can be written in the form of a over b, where a and b are integers and b is not equal to 0, is part of the set of rational numbers. In example 1, you're going to write each rational number as a fraction. So for got it 1a and 1b, write those as a fraction, pause the video, and press play to check your answer. For 1a, 4 and 2/3 can be written as 14/3. Remember that you multiply the whole number times the denominator and then add the numerator. That gives you 14, and then you keep the denominator. For 1b, 7 can be written as a fraction by putting it over 1. For example 2, you're going to be writing some decimals as fractions in simplest form. Many times when I read decimals, I take the shortcut and just say things like 0.64 or 0.125, when in reality the correct way to say them gives us information on how to write it as a fraction. So 64 hundredths is written as 64 over 100, and reduced, that's 16/25. For the second one, we have a mixed number, so we would pronounce that 9 and 675 thousandths, and then of course we can reduce that to 27/40. For the example 2 got it problems, try to press pause and do those two problems by yourself, and then press play to check your answer. For 2a, 0.84 is read 84 hundredths, and 84 hundredths reduces to 21/25. For 2b, 5 and 875 thousandths will reduce to 5 and 7/8. For 2c, 0.35 is pronounced 35 hundredths, and 35 hundredths reduces to 7/20. In example 3, you will be writing repeating decimals as fractions. And I really want you to take the time to look through this example so you can understand the process. When one digit repeats, we're going to multiply both sides by 10. If two digits repeat, we're going to multiply by 100. And so then if 3 digits repeat, we would multiply by 1,000. For the number of digits that repeat in the repeating decimal, you are going to multiply it by a power of 10. Eventually, you're going to get very good at figuring out how to write repeating decimals as fractions, but for now I really want you to understand the process of setting it up algebraically to prove why this process works. So let's try the got it problems at the bottom of the page. Since 0.42 repeating has 2 digits that repeat, we're going to multiply it by the power of 10 that has 2 zeros, which is 100. Start by writing n equals and then the repeating decimal. I usually write it 2 or 3 times. Then, since it repeats 2 digits, we're going to multiply both sides by 100. 100 times n is 100n. When you multiply decimals by a power of 10, you move the decimal over to the right, however many zeros there are. In this case, 100 times 0.42 repeating would be 42.4242, etc. Now we're going to subtract. When you subtract on the right-hand side, everything should line up and equal 0. 4 minus 4 is 0, and 2 minus 2 is 0, leaving 42 left on the right-hand side. On the left-hand side, we have 100n take away 1n, which is 99n. Now, to isolate the variable n, we will divide by 99. 99 divided by 99 is 1, leaving n by itself on the left. And on the right-hand side, we have 42 99ths. 42 99ths can be reduced. Both of those numbers are divisible by 3. 42 divided by 3 is 14, and 99 divided by 3 is 33. 14/33 is equal to 0.42 repeating. One key concept from section 3.2 is that a rational number is any number that can be expressed as the quotient a over b, where a and b are integers and b is not equal to 0. Here is a graphic for you to reference when you're thinking about our real number system, starting at our natural numbers, including our whole numbers, then adding in the integers, and then rational numbers. All rational numbers can be written as terminating or repeating decimals. However, we have some numbers that are not terminating or repeating, and those are called irrational numbers. A common irrational number that we all know is pi. The digits do not repeat. And although the second example here has a pattern, 787787778, it's not the same block of digits that repeats. For example 4, we will be using that diagram at the top of the page to identify all the sets of numbers to which each number belongs. -2 and 6/11 can be written as a fraction, so it is rational. Letter B, although there is a pattern in the numbers, there is a non-terminating and non-repeating block of numbers, so it is irrational. 45 is a natural number. It also is a whole number, an integer, and a rational number. For the got it problems at the bottom, 0 belongs to the group of numbers called the whole numbers. It also belongs to the integers, and it also belongs to rational numbers. For 4b, 1 and 4/5 can be written as 9/5, so it is rational. And for C, although there is a pattern, the pattern doesn't seem to continue, and it's not the same block of numbers that's repeating, so that would be irrational. For the higher order thinking problem on page 105, number 56 says to choose a repeating decimal in which 3 digits repeat. So I have chosen 0.359 repeating as an example, and we're going to write that as a fraction in simplest form. So we will do that right now by setting our variable equal to 0.359, and like I mentioned before, I write it a couple of times, so it'll be 359, 359, and then ... Because this repeating decimal repeats 3 numbers, we're going to multiply it by a multiple of 10 that has 3 zeros, which is 1,000. So 1,000 times x is 1,000x, and on the right hand side, when we multiply by 1,000, we're going to get 359.359359, and this isn't lining up very well in my video, but hopefully on your notes you can get them to line up a little bit better. When you're done writing that out, we're going to subtract these equations from each other. So what we have is 9 minus 9, 5 minus 5, 3 minus 3, and so forth and so on. What's left on the right hand side is 359. And on the left hand side we have 1000x take away 1x, which is 999x. And when we divide both sides by 999, we're left with 1x on the left hand side, and on the right hand side, when we divide by 999, we get 359 999ths. I will go ahead and check that using my calculator, and when I take 359 divided by 999, I get that repeating pattern. Again, the shortcut would be to just put the number of digits it repeats over that many nines, and so since 359 has 3 digits, I'm going to put it over 3 nines. But I do want you to know this process as well, so please make sure to have that in your notes. The second higher order thinking problem that I want you to do is number 57. 0.76 repeating is 0.767676 and so forth. And How that is greater than 76 cents is, if I think about money, this is 76 cents and this is 76 cents plus a little bit more. So when you extend that repeating decimal, it shows how it's greater than something that is terminating. Your homework for Lesson 3.2 is the Skills Practice Worksheet 1 through 27 odd. If after completing those problems and taking these notes you still have questions, please email me.